Questions 11 through 20 on the 2010 grade 12 AMC 12B. A palindrome between 1,000 and 10,000 is chosen at random. What is the probability that it is divisible by 7? Those numbers that are palindromes are of the form 1001 and so on. And then I just will put a few of these to illustrate what they look like. And it's pretty straightforward. Obviously, they are reading the same backwards and forwards. And if you go over to the 2000, it's pretty much the same story like this. And this keeps on going all the way until the very last will be the 9000s. And for that, of course, it will look very similar to the ones I just wrote. So now we have to figure out how many of these are divisible by 7. And the good news is that there's a pattern. Every single term that I wrote is of the form 1001A plus 110B. So for example, in this column, the A is just 1. I'll write it up here. But the B varies, right? For this one, the B is 0. For this one, the B is 1, and so on. And for this one, the B is 7, right? So 1001A, that is already divisible by 7. If you do that, you'll find that 1001 divides by 7 to give an integer. So that means this whole number is divisible by 7 if this is divisible by 7. Now, 110, is that divisible by 7? And the answer is no. So that means this B must be divisible by 7. And the only way that is possible is if B is equal to 0 or if B is equal to 7. And for every column, those are the only ones that will be divisible by 7. So that makes it pretty straightforward, right? So that means we have, in each column, we've got 10. And in each column, the ones that are divisible by 7, there's 2 of those. So therefore, 1 over 5 is the probability. So number 11, the answer is E. What does the value, for what value of x does this expression equal 40? So let's write this out, and let's first concentrate on just this guy right here. I think that will be sort of our starting point. I'll just call that A. And if you're familiar with log rules, obviously this, instead of log, writing all that out, I'll just write A to match this one right here. And then this one, which is the log of x squared to the base 4, you can write as log of x to the base 4. The 2 comes out front, and very similarly, the 3 comes out front for that, and the 4 will come out front for this one, based on log rules. And this is equal to 40, and let's not forget the very first one. That's going to be an exponent of a half, so that's the log of root of x to the base root 2. Okay, now, this is where the coolness begins. Each of these can be written in terms of A, and that's where having a good knowledge of logs comes in handy. This one is just A over 2, and don't forget the 2 in front. This one is A over 3, and don't forget the 3, and this one is A over 4, and the 4 goes out front. This one was just A, which I had previously substituted. This one is 2A, and don't forget the half. So now if you multiply through, you get A plus A plus A plus A plus A, and that is equal to 40. So that means 5A is equal to 40, and therefore A is equal to 8. Okay, we still don't know what x is. Well, that's where this comes in. The log of x to the base 2 is 8, and therefore 2 to the power of 8 is x. And 2 to the power of 8 is equal to 256. So number 12, the answer is D. In triangle ABC, the cos of 2a minus b plus the sine of a plus b equals 2, ab is 4. What is the length of BC? So let's just draw some triangle, and it's ABC. You have A, B, and C. And they give me that AB is 4. And that's all they give me. And then we have this equation. Now, if you recall, the sine or cosine of anything, whatever it is, can only be between -1 and 1. Correct? So whether it's the sine of something or the cos of something, these are its boundaries. And I'm sure you've seen the graph of sine x and cos x many times to understand that. So we're taking the cos of something and adding it to the sine of something, and it equals 2. Well, the only way that's possible is if both of those are equal to 1. So for example, this right here is 1 and this is 1. That's the only way you can get a sum of 2. Both of them have to have the maximum possible sum. So that means cos of 2a minus b is equal to 1. And if that is true, that means 2a minus b is equal to 0, because the cos of 0 is equal to 1. And similarly with this guy, the sine of a plus b is also equal to 1, and therefore a plus b is equal to 90 degrees, because the sine of 90 is equal to 1. So there you go. We have to now use these two equations to solve for a and b. So let's see, if we add them, if this is equation 1, this is equation 2, and if you add them, you get 3a is equal to 90, and therefore a is equal to 30. So that means this angle is 30. Now let's figure out b. Well, b you can just substitute back into any of those. That means 30 plus b is 90. So b is 60. So this is 60. And then the sum of the angles of a triangle add up to 180, so therefore C must be 180 minus 90, which is 90. Okay, so that's a 30, 60, 90 triangle. And like any 30, 60, 90 triangle, the ratio of the sides are 1, 2, and root 3. So what do they want us to find? BC. So BC over AB, in terms of the ratios, will be 1 over 2. And therefore BC is AB over 2, and AB, they tell me, is 4. So 4 over 2, and that is 2. So BC is 2, and therefore number 13, the answer is C. Let A, B, C, D, and E be positive integers with A plus B plus C plus D plus E equal to 2010, and let M be the largest of the sums A plus B, B plus C, C plus D, and D plus E. What is the smallest possible value of M? We have A plus B, B plus C, C plus D, and D plus E. And one of these is M. Now I don't know which one is M. So I don't know, I'll just call this one M. If that is the case, and they have told me that M is the largest of those, then that means M is greater than A plus B. M is also greater than B plus C, and M is also greater than D plus E. So now let's take a look at this equation. They have told us that the sum of all those is equal to 2010. Well, M is greater than A plus B, so M is greater than this A plus B right here. M is also greater than D plus E, so M is greater than this D plus E. And M is greater than B plus C, which also means that M must be greater than C, since all of them are positive. So M is greater than this C here. So that means that if you add these up, 3M is greater than all of these, correct? And 3m therefore is greater than 2010. Now, dividing through by 3, you get 670. So m must be greater than 670. So the smallest it could possibly be is m equal to 671. So that's a bit abstract. The other way of doing it is by plugging in numbers. That's, I think, a little harder to do, but easier to understand once the numbers are placed in front of you. And those numbers are 669, 1, 670, 1, and 669. All these numbers, when added together, will equal 2010. But watch what happens with the a plus b, all these guys. A plus b becomes 670, b plus c is 671, c plus d is 671, and d plus e is 670. So the largest is 670. And what's interesting about that is that makes me think that there's a tie here. M is the largest, but it's not the sole largest. So a little bit of a, I don't know what to say here, but I guess the wording, we have to sort of take into account that it didn't tell us that it could be a tie. So that means that this m right here is actually greater than or equal to this b plus c, right? Because in our case, we got it to be equal. So it's just a minor little thing that I just wanted to point out. But in any case, the answer is 671. Hope you understood that. So number 14, the answer is B. For how many ordered triples x, y, z of non-negative integers less than 20 are there exactly two distinct elements in the set I to the x, 1 plus I to the y, and z, where I is the square root of -1? Let's first explain this question. What do they mean by exactly two distinct elements? It means, for example, if you have a set x, y, z where you have 1, 2, and 3, that is 3 distinct elements. But if you have a set that's 1, 2, and 2, then there's 2 distinct elements. There's 2 same elements, but 2 distinct. So that's what they mean. And then, of course, something like 2, 2, 2 would be only 1 distinct element, and 3 the same. So that is what they're asking us. Now, 2 distinct elements is the same as 2 the same if there's 3 elements in the set. So I just want to make a quick table. I of x, 1 plus I to the y, and z. Now, I want to explain this carefully. The explanation is going to be probably a little bit longer than you need, but I just wanted to ensure that you understand it. We have to choose integers less than 20, and they're non-negative. So our choices are basically from 0, 1, all the way up till 19. Those are the only choices we have. And for each of these, we have to figure out what are the possible values. So for I to the x, if we start with I to the 0, right, because x can be anything from 0 to 19. So we start with I to 0, that is equal to 1. And then I to the 1 is equal to just I. And then I to the 2, I squared, is equal to -1. And then I to the 3rd is equal to -I, like that. Now the good news is that for this particular part of the question, these just keep repeating. So if you keep doing this all the way I to the 4th and I to the 5th and so on, this pattern just keeps repeating. This pattern of 1I, -1, -I. So you don't necessarily need to know what they all are. They're all the same. So for example, I'll just do a few more. So this one, it's the same pattern. It'll be 1, this one will be I, this one will be -1, and this one will be -I, and so on. It just keeps going like that. So we only have 4 different possible values. 1 plus I. This one, what are the possibilities for y being anything from 0 to 19? Well, if it's 0, that's easy, that's 1. If y is equal to 1, this just becomes 1 plus I. If you have 2 for the exponent, then it becomes 2i. And you can expand that out and verify. If it's 3, then this becomes negative 2 plus 2i, and so on, right? It just kind of keeps on going. Now, we have to understand the fact that a lot of these are going to be just complex numbers, right? And complex numbers are never going to match up with anything else. Why? Because z is just integers. This is just integers like 0, 1, 2, all the way up to 19. Most of these are going to be complex numbers. Now you say, well, what about these guys? There's complex numbers there. Won't they match up? And they would, but unfortunately, these ones, almost all of them, are going to have a very large numbers that are going to be much bigger than 1. And already you've seen that we've already gone up to 2. And if you keep going, you'll see that that's it. You're never going to get 1s again. So this was 3. This 4 will be a negative 4. And then if you do this to the power of 5, it will be negative 4 minus 4i, and so on, right? Now, the hard part about this question is there was one value in this list that will match the z value, other than the one that is pretty obvious. And that one is 16. And that happens when you have an exponent of 8. And that's it. After that, it will be a whole bunch of complex numbers that are very large, and you won't get any number in this range anymore. So here we go. And z, of course, can be anything from 0, 1, to all the way down to 19. Okay? So now, let's talk about making a set that has 2 distinct elements. So what are the possible choices we can have for x, y, and z? So our elements are I to the x, 1 plus I to the y, and z. And we want 2 distinct elements. So let's just start with the very first one. If the first one is 1 and the second one is 1, then I've got 2 the same. And if the z is different, then it will be 2 distinct elements. Now z can be anything from 0 and then 2 to 19. It can't be 1, because if it's 1, then all 3 are the same. If z is anything like 0 or 2 to 19, we will have 2 distinct elements. So how many ways of doing this? Well, we have 19 possible choices for z. So there's 19. But keep in mind that this is only one time. So therefore, there's only one way of making that a 1. But this, I to the x, is 1 several times. It happens when you have I to the 0 as listed. It happens when we have I to the 4 as listed. It also happens when you have I to the 8. And then you have I to the 12. And when you have I to the 16. So there's 5 values of x that give you that. And I'll just list them. So when x is 0, 4, 8, 12, and 16. So there's 5 values. So this 19, we have to multiply by 5. And that is 95. And that is how many ways this scenario can be done of a 1 plus something else. Okay, so I hope that makes sense. All right, let's move on to the next one. The next way of making this, so that you have 2 distinct elements, exactly 2, is this stays a 1, and this becomes a 1. So, as before, how many ways are there to do this? Well, let's talk about this guy. What can this be? It can be anything except this 1. So since there's 20 possible values of this expression, and this is the only one I can't put, I've got 19 possible. And I'm not going to list them all, but some of them are listed here, right? For z, there's only one possible way of putting a 1 there. It's just the integer 1. But what about for I to the x? Well, very similar to what I did up here. There's 5 possible ways that I to the x could be equal to 1. It's when x is equal to either 0, 4, 8, 12, or 16. So in a very similar way, we get 5 here. And the number of ways of creating this is, of course, again, 5 times 19, which is 95. And the good news is the last two are very straightforward. It's when you have 1 for this and 1 for that. Z can be 1, of course, you just choose 1. But I plus 1 to the power of y is 1 only once when x is equal to 0. So there's only one way of doing this and only one way of doing that. But what about this guy here? What can that be? It can be anything except 1. And it's 1 5 times. 1, 2, 3, 4, 5. And there's 20 possible values for I to the x. So 20 minus 5, which is 15. That is what goes there. So 1 times 1 times 15, there's 15 of those. And the last one is a tricky one. That's this guy right here. When I plus 1 to the power of y is equal to 16. And when z is 16, and this is anything other than 16, but all of them are other than 16. If you look at the I to the x column, it's never going to be 16, right? So all 20 of those, I'll put that in brackets, all 20 of those will fit. So this is one way of doing that, one way of doing that, and 20 ways of doing that. So 20 here. And then we have to add up these guys to get the total. So 95 plus 95 is 190 plus 35, 225. If you add up this, 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 and this. So the answer to number 15 is D. Positive integers a, b, and c are randomly and independently selected with replacement from the set 1 to 2010. What is the probability that a, b, c plus ab plus a is divisible by 3? A, b, c plus ab plus a is divisible by 3, so it will be 3k. And immediately you can factor, as you can clearly see, and if you do, you get this expression. Now we want to ensure that that is divisible by 3. So there's a couple of cases, case 1 and case 2. The first case is when a itself is divisible by 3. If it is, then this whole expression will be divisible by 3 regardless of what this is. So a has to be a multiple of 3, and therefore out of those 2010 numbers, we have to figure out how many multiples of 3 are there. Well, we can easily do that by taking 2010 and dividing by 3, and that is 670. So 670 of these numbers are multiples of 3. 3, 6, 9, 12, and so on. So 670 out of the 2010 numbers are multiples of 3, and that is 1/3. So that takes care of case 1. Case 2 is when a is not a multiple of 3. So it's not 3, 6, 9, 10. It's like 2 or 5 or 11 or something like that. And this guy is a multiple of 3. So bc plus b plus 1 is equal to some multiple of 3. All right? So both of these have to happen to get a unique probability for this case. Okay, well, this guy is pretty straightforward. If a equals 3n has a probability of 1/3, a does not equals 3n has a probability of 2/3. And then this, we have to figure out the probability of that. and that will be some p. And then at the very end, my total probability is going to be this 1/3 plus this 2/3 multiplied by that p, whatever I get for my p-value. So now we have to concentrate on trying to get this p. Alright, so this expression I can factor out a b, and I get c plus 1, and I can put the 1 on the other side to get 3n minus 1. And now I'm going to use mod. If you're not familiar with mod, I'll give you a quick example. Let's say you have 8 mod 3. And what does that mean? It means that when you take 8 and divide by 3, what is the remainder? Well, the remainder is 2. So that is equivalent to 2. Similarly, if you have, let's say, 4 mod 3. Well, if you take 4 and divide by 3, what's the remainder? It's 1. So this is what I'm going to use to figure this out. If this is the case, that holds true in 2 separate scenarios. The first scenario is taking into consideration that 3 to the n minus 1, if you take the mod of it, and I'm going to use mod 3 since I'm looking at things that are divisible by 3. If you take that to the mod 3, that is equal to 2 mod 3. Why is that? Because if you take 3n minus 1, any number of that form, so for example 5, 8, all of those are of the form 11, all of those are of the form 3n minus 1, and you divide by 3, the remainder is always going to be 2. And that's why 3n minus 1 is equivalent to 2 mod 3. Now 2 mod 3 has to match with this guy. And there's only 2 possible ways that can happen. The first is when b is equivalent to 2 mod 3 and c is equivalent to 0 mod 3. Because if you do that, you'll get 2 here, then you'll get 0 here, and then 0 plus 1 is 1, and 1 times 2 is 2, and that will match this 2. The other way of matching this is if b is equivalent to 1 mod 3 and c is equivalent to 1 mod 3 also. So for example, that would put in this situation a 1 here, a 1 here. 1 plus 1 is 2, and 2 times 1 is 2, and that matches that 2. So now we have to figure out the probabilities of each of these. For b to be equivalent to 2 mod 3, that means it's all the numbers of the form like 5 and 8 and 11. And for if a list like this, it's basically 1/3 of those numbers. 5, 8, 11, like that. So the probability of this is 1/3. This basically says that c is equivalent to 0 mod 3. So that means that c is divisible by 3 because you have a remainder of 0 when you divide by 3. So very similarly to how we did it over here, of all the numbers from 1 to 2010, 1/3 of them are divisible by 3. So the probability here is also 1/3. So we want this and this. So this probability will be 1/3 times 1/3, which is 1/9. Now we get to this part. Very similarly, if b is equivalent to 1 mod 3, b is something like 4 or 7 or 10, and the probability of getting that out of a list from 1 to 2010 is 1/3. And very similarly, this guy, it's the exact same. It will also be 1/3. So this probability is 1/3 times 1/3, which is 1/9. So this p that I put here that I'm going to put here is this plus this. And that plus that is, of course, 2 over 9. So now this becomes 1/3 plus 2/3. And my p is this plus that, which I have stated is 2 over 9. And here we go. So that's going to be 1/3 plus 4 over 27. And if you do the addition, it becomes 13 over 27. The overall probability for this question. So number 16, the answer is E. The entries in a 3x3 array include all the digits from 1 to 9 arranged so that the entries in every row and column are in increasing order. How many such arrays are there? So we have 3 scenarios. The first scenario is when you have a 4 in the middle. So the middle number will be 4. The second scenario is when the middle number is a 5. And the third scenario is where the middle number is a 6. Now, the important thing is that if I were to draw this, you will notice that the 1 and the 9 always have to go in those positions. That's the only way this can work. The 1 starts it off and it all ends up ending in the 9. Now what we have to do is fiddle around with a few other selections. I'll put the 2 here and a 3 here, and there's a few other variations, but the 4 we have set in this case to go in the middle. And then the 2 and the 3 I will set here. And other scenarios I will do later. So this is sort of my starting point. All right, so now what we have to do is figure out how many variations are there for each of these. The first 3, I'll put the 8 here. And the next 3, I'll put the 8 down here. And now for the remaining 3, I've only got 3 numbers left, so I can arrange them in, I guess, 3 different ways. Either 5, 6, 7 here. Either 5, 6, 7 like that. Or 5, 6, 7 like that. All right, that takes care of those. And then the ones where the 8 is in the bottom, again, either 5, 6, 7 like this, or 5, 6, 7 like that, or 5, 6, 7 like that. Okay? And then now the next 6, the good news is that you have something called diagonal symmetry. And diagonal symmetry makes your life very easy because all you have to do is just flip it in the diagonal. And if you do, you get the next set of numbers. So I'll just do the first couple and you'll see what I mean. If the 1, 2, 5 were here, it'll now be here, diagonal symmetry. If the 1, 3, 6 was here, it'll be 1, 3, 6 here. The 4s and 9s don't change, but then the 8 and the 7 do. So you see how it diagonal symmetry just flipped that? And very similarly with diagonal symmetry, you can just get the other ones. I'm just taking the next one, which is right here, and just kind of doing a mirror reflection like that. So 1, 2, 6 goes there, 1, 3, 5 goes there. The 4 and 9s don't change because they're right on the diagonal, but the 7 and 8. So you can do that for the other 4, and I'll just write those in. So there you go. So how many did we get? We got 12 here, right there. So far so good. Now we got to go with the ones where the middle number is a 5. All right, so let's draw some of those. And as before, the 1 and the 9 have to go in those spots. That is the only way this will work. but now the middles are 5s like this. And we'll put in the first few scenarios. This is the first scenario. This is another scenario with the 3 there and the 8 down here. And this is another scenario with the 3 and the 8 here. And here's another scenario with the 3 there and the 8 over here. And the good news is that since you only have 2 empty, sorry, there should be an 8 here, like this. So the first one, there's only 2 missing, right? There's 6 and a 7 missing. So the scenarios are 6 and 7 here, or a 6 and a 7 there. So that means for this first guy, there's 2 possible choices. For the next one, there's 3 digits missing, and those 3 can be arranged in 3 ways. For example, the 4, 6, and 7. So you can have 4, 6, and 7 like that. Or you can have the 4, 6, and 7 like that. Or you can have a 4 and the other 2 like that. So as you can see, there's 3 ways of doing that. Similarly, since there's 3 here, there's 3 ways of arranging the missing numbers. And here there's only 2, so there's 2 ways. Well, actually here it's a little tricky because there's only a 6 and a 7. So really there's only 1 way of doing that. So that's a little tricky, I think. So if you add these up, you get 1, 2, 3 plus 6, which is 9. And again, by diagonal symmetry, you will get an additional 9. So this scenario, you get 18. And then when the middle is 6, the good news is that, and I'll let you figure this out, I don't want to go through all this all over again, this whole thing, is that it's pretty much the same as case number 1. These guys. Pretty much the same. And because it's the same, it produces 12. So there you go. These are the grand total, 12, 12, and 18, and that is 42. So the answer to number 23 is D. A frog makes 3 jumps, each exactly 1 meter long. The directions of the jumps are chosen independently and at random. What is the probability that the frog's final position is no more than 1 meter from its starting position? So let's draw a graph and let's talk about this question. So first, we will denote some positions. I'm going to draw a circle, and that circle kind of shows where this frog is kind of. And I don't know where the frog is, but I'll just say he's right there. So I'll just put F for frog. And then that's its starting point, and this is its second point. It's obviously going to go 1 meter in some direction. So if it does, let's just say it ends up there. We don't know where it's going to go, but I think that's a pretty good place. So I'll call that point 2. And then it's going to go 1 meter somewhere. Let's just say it goes here. I'm going to call that point 3. And then finally, it's going to go 1 meter somewhere, but the next place that it goes is anywhere in a 1 meter radius from P3. So it's something like this. Another circle that has a radius of 1, like that. And the ending point is anywhere on that circle. So I have no idea, so let's just say that's the ending point. So I'll call that P4. So for example, this frog started here, it went here 1 meter, because that's the radius of the circle. It went here 1 meter, also representing the radius of the circle. And then it goes here 1 meter, also representing the radius of the circle. Now, the question is saying, what is the probability that the frog's final position is no more than 1 meter from its starting position? Now, in this particular question, is he 1 meter less or more? Well, he's obviously much more than 1 meter. So this is a scenario that they don't want. They want the probability that he ends up somewhere 1 meter or less from his starting position. So we have to start labeling this. And this frog's first position, I'm going to use trigonometry and label it cos theta and sine theta. Like that. That's this position right here. And my theta is anywhere between 360 degrees and 0. Right? It's anywhere from 0, which is here, all the way going around 360. Okay? So far, so good. And then this P, this position right here, I basically put it at the origin, so that's 0, 0. And then P3 I put here, which is 1, 0. And then P4, I put it here. It could be anywhere, right? It could be anywhere on the circle. It could be here, or it could be there, or whatever. So let's just label that. But we're also going to use trigonometry. We have to add 1 to the x-coordinate, right? Or whatever coordinate system that you're using. And because we went from here to here, and that's a distance of 1. And then it's going to be the cos of theta, or let's use a different letter. Let's use beta, like that. And the sine of beta. All right. And then, of course, beta, we have to give a boundary. It's very similarly anywhere between 360 degrees and 0 degrees. Okay? So now we have to figure out a few scenarios. So the first condition is when theta is equal to 0. When theta is equal to 0, that means this frog is somewhere. He's right here. This point right here. So I'll call that 1. And then when theta is 0, we have to figure out when is the condition of the question met, that the frog is no more than 1 meter from its final position. And if you look at the diagram, for all values of beta, no matter what beta is, he's always going to be within 1 meter. Okay, so that one was pretty straightforward. What about when theta is equal to pi? Where's the frog then? Well, theta is equal to pi, which is 180 degrees, and I prefer to write 180. I've always preferred to write degrees rather than radians. And that means the frog is here now. We'll call that position 2. Now, for what values of beta is the condition going to be true? It's only true when beta is equal to 180. So that means when the frog's final position is here. So we'll just call that frog 2. So I hope you understand that. Now, what about all the other scenarios? We talked about when theta is 0 and theta is 180. Now we have to talk about all the thetas between 0 and 180. So all of these guys. So when theta is between 180 degrees and 0, when is this condition met? It's only met when beta is less than or equal to 180 or is greater than or equal to theta. And then finally, we have to talk about this part, which is when theta is greater than 180 but is less than 360. In that scenario, this condition is met when beta is less than or equal to theta, but greater than or equal to 180. So now what we have to do is combine all of this into a graph, and then we can figure out the probability. So we'll draw the graph, and this is going to be beta, and this is going to be my theta, and my absolute boundaries for beta, we only need to look at the first quadrant to figure out the probability, and the boundaries in the first quadrant are 0 to 2 pi. So if I label this, let's say 2 pi right here, right there, that point right there. And then very similarly for theta, our boundaries are 0 to 2 pi as well, as I have previously stated. Now that's my total region. We have to figure out where these guys fall, the combination. Well, they fall first and foremost when beta is equal to 180, which is pi. I know I'm mixing radians with degrees, but that's okay. It just makes the math a little bit easier. So approximately here. That takes care of this guy right here. But then all of B is basically from top to bottom, like that. But now we're interested in this one here. Beta is less than 180 degrees, which is 2 pi, but it's greater than theta. So what that means is that we have to now look at a line that represents the following. Theta is equal to beta, this line right there. And if you look at this, it's basically telling me that beta is greater than theta, but less than 180, which is pi radians. So in this diagram, it's this region right here. And then now, if we look at this in a very similar way, it's telling me that beta is less than theta, but it's greater than 180. So it's this region right here. So now to figure out the probability of this question, we have to figure out the area of those shaded regions and divide by the total area. So the probability, area of the shaded region, it's 2 times 2 triangles, 1/2 base times height. The base is going to be from here to here, which is half of 2 pi, which is just pi. And the height is from there to there, which is pi. And then the total is just 2 pi times 2 pi, like that. So this gives me pi squared over 4 pi squared, and then the pi squareds cancel to give a final probability of just 1 over 4. So number 18, the answer is C. A high school basketball game between the Raiders and the Wildcats was tied at the end of the first quarter. The number of points scored by the Raiders in each of the 4 quarters formed an increasing geometric sequence, and the number of positions scored by the Wildcats in each of the 4 quarters formed an increasing arithmetic sequence. At the end of the 4th quarter, the Raiders had won by 1 point. Neither team scored more than 100 points. What was the total number of points scored by the 2 teams in the first half? So you have quarter 1, quarter 2, quarter 3, and quarter 4. And we have the Raiders and we have the Wildcats. Now the Raiders, their score is in the form of a geometric sequence. So that basically means it's A, AR, AR squared, AR to the 3rd. The Wildcats, their scores are in the form of an arithmetic sequence. So that's A plus D, A plus 2D, and A plus 3D. Now, how do I know that both of them have A? Because they tell you that they were tied at the end of the first quarter. So at the end of the first quarter, their scores were the same. So that's why it's A and A. So what do they want us to figure out? What was the total number of points by the two teams in the first half. So they want you to figure out this total. So obviously we need to figure out the numerical values of A, R, and D. Okay, so this sentence is what we have to concentrate on. At the end of the fourth quarter, the Raiders had won by 1 point. So that means that if you add up all the scores at the end of the fourth quarter, the Raiders win by 1. So this is 1 more than the total of the Wildcats score. So A plus 2D, A plus 3D, and then a final 1 at the end. So let's add this up. Let's see if we get anything that helps us. We only have one equation here, so I'm guessing that there's going to be a lot of inspection involved. This is 4A plus 6D plus 1. Yeah, we only have one equation to try to figure out 3 variables. Normally you need the same number of variables as equations. So this is going to be based entirely on inspection. They tell me a little bit of a clue though, not a big clue, but neither team scored more than 100 points. So that means that the numbers are going to be relatively small. And in particular for R. So I'm going to start with R equals 1. But R can't equal 1 because it's an increasing geometric sequence. Increasing means that R is greater than 1. Okay, no problem. Let's start with 2. If R is 2, let's see what happens. If I sub R equal to 2, I get 1 plus 2 plus 4 plus 8. And this doesn't really change, 4A plus 6D plus 1. But this becomes, let's see here, 15A. 15A is equal to 4A plus 6D plus 1. And that becomes 11A is equal to 6D plus 1. Now let's see what we can substitute to get integer solutions. When you fiddle around with this, it'll work when A is 5 and when D is equal to 9, right? Because you have 55 on this side, and this side you'll have 6 times 9, 54 plus 1, which is also 55. So there you go. With a little bit of plug and play, we got the values for R. I had said R equal to 2, right? 5 for A and D for 9. So now we can go back and figure out their score in the first half. The first half score is going to be A plus AR plus A plus A plus D. So that's going to be, let's see here, 5 plus 5 times 2, 10, plus 5 plus 5 plus 9. And that looks like 10, 20, 25, 34. So number 19, the answer is E. A geometric sequence AN has A1 equal to sine x, A2 equal to cos x, and A3 equal to tan x for some real number x. For what value of n does AN equal 1 plus cos x? A1, A2, A3, A4, and then all the way down to AN is this sequence. And they have told me that A1 is sine x, A2 is cos x, A3 is tan x, and AN they have also given me is 1 plus cos x. Now because it's a geometric sequence, these are of the form AR squared, AR to the third for A to the fourth, and then finally AR to the n minus 1. So like any geometric sequence, if you take the second term and divide by the first term, it gives you just R, right? And very similarly, if you take the third term and divide by the second term, you get R. So we can immediately sort of do that and get a value for R. So cos x divided by sine x is equal to R. And if I take the third term and divide by the second term, I also get a value for R. So R basically, if you just look at this one, that looks like 1 over tan. Okay, so far we have a little bit of information. Now, the next part is I'd like to concentrate on A4. I have a feeling that A4 is going to help me. A4 is AR to the power of 3? Well, that's really just AR squared times R. AR squared is tan x, that's given to us in the question, and R, I just figured out, was 1 over tan x. So that means that A to the 4th is just 1. So that's very helpful. So put that in red there. Okay, so now we can move forward with this question and try to figure out when is the term going to be 1 plus cos x for what value of n. Well, we got this to be r, we got that to be r, so let us set them equal to each other. If we do, we get cos of x over sine of x is equal to the tan of x over the cos of x. Now this is just cos of x, and I can multiply that by sine all over cos, and tan of course is just sine over cos, like that. And then I can bring all the coses over, and this becomes cos to the power of 3x sine x squared. But instead of writing sine x squared, I can use the fact that cos squared plus cos x squared plus sine x squared is equal to 1. You remember that identity? So that allows me to isolate and just put something in terms of cos. It just makes it better if we have just one variable, like that. And then we can now manipulate this. Let's see here. If you put everything on one side that has cos in it, you get cos to the power of 3x plus cos squared x is equal to 1. Factor out a cos squared x, and you'll just get cos x plus 1. And there we go. This is starting to look very much like what we want. 1 plus cos x is therefore 1 over cos of x squared. Okay? And now we just go back to the original terms, because this looks very familiar to the terms. I've got a 1 here, I've got a cos x here. And basically what that means is if I did a4 divided by a2, that's just 1 over cos x, right? But a4 is ar to the power of 3, and a2 is ar. So if you write it like that, the a's cancel, one of the r's cancel, and all you get left with is 1 over cos x is equal to r squared. But we don't have that. We have squared, so I can just square both sides. And therefore I get 1 over cos squared x. So that means that 1 plus cos x is just r to the power of 4. And that's it. We now have one final step, that we have to recognize that this is really the same as writing 1 times r to the 4, and 1 is the same as ar3 and times r to the 4, and that is of course ar to the 7. And ar to the 7 means that this is the 8th term, a8, because that would be equivalent to ar and minus 1, which is 7. So there you go. N is 8, and therefore number 20, the answer is E.